Imagine holding a teaspoon of matter so dense that it weighs billions of tons. This might sound like something out of a science fiction novel, but it's a real phenomenon in the universe. Such an extraordinary density is found in neutron stars, which are the remnants of massive stars that have undergone a supernova explosion. Neutron stars are the collapsed cores of these massive stars. When a star much larger than our Sun reaches the end of its life, it explodes in a supernova, leaving behind a core that is incredibly dense. This core is what we call a neutron star. These stars are not just remnants, they are among the most fascinating objects in the cosmos. Neutron stars are among the most extreme objects in the cosmos, pushing the boundaries of physics as we know it. They are so dense that a single teaspoon of neutron star material would weigh about 1 billion tons. This extreme density is due to the fact that the core has collapsed to the point where protons and electrons have merged to form neutrons. Neutron stars are born from the death throes of giant stars, much more massive than our own Sun. These stars live fast and die young, burning through their nuclear fuel at a rapid pace. When they run out of fuel, they can no longer support themselves against the force of gravity. When these stellar behemoths exhaust their nuclear fuel, they can no longer support themselves against the relentless inward pull of gravity. The outer layers of the star are blown away in a supernova explosion, while the core collapses under its own gravity. The core collapses catastrophically, compressing the star's matter into an incredibly small and dense object. This process happens in a fraction of a second, creating a neutron star that is only about 20 kilometers in diameter but contains more mass than the Sun. The result is an object with a gravitational field so strong that it warps space and time around it. The formation of a neutron star is a dramatic event, one that marks the end of a massive star's life cycle. This process is not just a simple transformation but a cataclysmic event that reshapes the very fabric of space around it. Imagine a star many times the mass of our Sun, its core a fiery furnace of nuclear fusion. This core is where the star's energy is produced, a relentless process of fusing hydrogen into helium, releasing immense amounts of energy in the form of light and heat. As the star ages, it burns through its fuel, eventually reaching a point where it can no longer produce enough energy to counteract gravity. This is a slow and inevitable process, taking millions or even billions of years, depending on the star's initial mass. The core collapses in on itself, a cosmic implosion of unimaginable power. This collapse happens in a matter of seconds, releasing a tremendous amount of energy and often resulting in a supernova explosion, one of the most powerful events in the universe. This collapse compresses the core's protons and electrons, forcing them to combine and form neutrons. The density of the core increases dramatically, and the matter is squeezed into a state where the usual atomic structures can no longer exist. The result is a sphere of almost pure neutron matter, a neutron star. These stars are incredibly dense, with a single teaspoon of neutron star material weighing billions of tons. This process packs the mass of a star into a sphere only a few miles across, creating an object of unimaginable density. Neutron stars are so dense that their gravitational pull is immense, warping space and time around them. Some neutron stars become pulsars, rotating rapidly and emitting beams of radiation from their magnetic poles. These beams sweep across space like cosmic lighthouses, and when they point towards Earth, we detect them as regular pulses of radio waves. In some cases, neutron stars exist in binary systems, orbiting another star or even another neutron star. When these neutron stars collide, they create gravitational waves, ripples in the fabric of space-time that can be detected by observatories on Earth. These collisions are also responsible for creating some of the heaviest elements in the universe, such as gold and platinum, through a process known as a kilonova explosion. The death of a star, therefore, leads to the birth of new elements, continuing the cycle of cosmic creation and destruction. To grasp the sheer density of a neutron star, consider this. A teaspoonful of neutron star material would weigh roughly the same as Mount Everest. Picture that for a moment, the weight of the world's highest mountain compressed into a volume smaller than a sugar cube. This extreme density results from the crushing force of gravity during the star's collapse. The atoms themselves are squeezed together, their electrons forced into the nucleus to combine with protons, forming neutrons. The result is a state of matter unlike anything found naturally on Earth. The surface of a neutron star is a place of intense gravity and searing heat. Imagine a world where the gravitational pull is billions of times stronger than Earth's, where even light itself struggles to escape. The surface temperature can reach millions of degrees, hot enough to vaporize any known substance. This intense gravity arises from the neutron star's incredible density, packing a star's worth of mass into a tiny volume. The gravitational pull is so strong that it warps the fabric of space-time, creating bizarre effects that challenge our understanding of physics. Section 5. The Dance of Gravity. The immense gravity of a neutron star is not its only extraordinary feature. Neutron stars also rotate incredibly rapidly, some spinning hundreds of times per second. This rapid rotation is a consequence of the conservation of angular momentum during the star's collapse. Imagine a spinning figure skater pulling their arms in close to their body. Their spin accelerates. Similarly, as a star collapses, its rotation rate increases dramatically, resulting in the dizzying spin of a neutron star. Section 6. The Inconceivable Pressure Cooker. Deep inside a neutron star, the pressure and temperature reach unimaginable levels. These stars are the remnants of massive stars that have exploded in supernovae, leaving behind a core so dense that a single teaspoon of its material would weigh billions of tons on Earth. The gravitational forces at play are so extreme that they crush protons and electrons together to form neutrons, creating a star composed almost entirely of these subatomic particles. The pressure at the core is so intense that it forces neutrons to be packed closer together than they would be in the nucleus of an atom. This density is so great that it defies our conventional understanding of matter. Imagine a city-sized object with the mass of the sun, where the matter is compressed to the point that it becomes a single giant atomic nucleus. This creates a bizarre state of matter unlike anything we can create in a laboratory. In these extreme conditions, matter behaves in ways that challenge our current theories of physics. The core of a neutron star is a place where the known laws of physics are pushed to their limits, and new exotic states of matter may emerge. This extreme environment pushes matter to its limits, creating a cosmic laboratory where the fundamental laws of physics are put to the ultimate test. Scientists believe that studying these stars can provide insights into the behavior of matter under the most extreme conditions, potentially revealing new physics beyond the standard model. Studying neutron stars allows us to peer into the heart of matter, exploring the nature of reality at its most fundamental level. By understanding these celestial objects, we can gain a deeper appreciation of the universe's complexity and the forces that govern it. The research conducted on neutron stars not only expands our knowledge of astrophysics, but also has the potential to unlock new technologies and applications here on Earth. Section 7. Beyond the periodic table. The matter inside a neutron star is unlike anything we encounter in our everyday lives. It's not simply a collection of atoms, it's a sea of neutrons packed together with unimaginable density. This neutronium, as it's sometimes called, behaves like a single, giant atomic nucleus. This exotic state of matter has profound implications for our understanding of nuclear physics. By studying neutron stars, we can gain insights into the forces that hold atomic nuclei together and the behavior of matter under extreme conditions. Section 8. The Universe. A tapestry of wonders and dangers. The existence of neutron stars reminds us of the incredible diversity and power of the universe. These cosmic remnants serve as a testament to the awe-inspiring forces that shape the cosmos, from the birth of stars to their dramatic deaths. Yet, these celestial objects also highlight the dangers lurking in the vast expanse of space. The extreme conditions found within and around neutron stars are a stark reminder that the universe is not a benign place, but a realm where powerful forces hold sway. Section 9. An invitation to explore. As we continue to explore the cosmos, we are bound to encounter even more bizarre and wondrous objects. Neutron stars, with their mind-boggling density and extreme conditions, are just one example of the universe's capacity to surprise and amaze us. Their study offers a glimpse into the fundamental nature of matter and the workings of the universe at its most extreme. The journey of discovery is far from over, and the cosmos beckons us to unravel its countless mysteries.